We are going back to the moon. Not someday, not in theory, right now. And for the first time since Apollo, we are not just asking how to get there. We're asking where we're going to stay. Shackleton Crater, the first foothold. When we say we're going back to the moon, that sounds like a destination. But the moon isn't one place. It's a collection of very different environments, and where we choose to land will shape everything that comes after. Today we'll be looking at Shackleton Crater and the lunar South Pole more generally, the leading contenders for humanity's first long-term footholds beyond Earth. We'll also be discussing several other prime spots across the moon, from the wide volcanic plains of the equator to the radio silent reaches of the far side, and asking a simple question: where should we actually build our first base? And this isn't a theoretical question. NASA's Artemis program and similar efforts from other space agencies are actively planning those first missions right now. The decisions being made over the next few years will determine not just where we land, but how we expand beyond Earth for decades to come. When people talk about returning to the moon today, they are usually talking about one place, they don't say it directly: the South Pole, specifically the region around Shackleton Crater. That can seem a bit strange at first. Every Apollo mission landed near the equator, and for good reason. From an engineering standpoint, the equator is easy mode. You get the most efficient launch and return trajectories, and you're surrounded by wide, flat volcanic plains that are relatively forgiving to land on. So why is Artemis aiming for one of the most difficult places on the moon? And why a crater? Because lunar craters are not like the ones we're used to on Earth. There is no wind, no rain, no erosion, and no biology to wear them down. A crater on the moon stays sharp, jagged, and often unstable for billions of years. Steep walls, fractured terrain, and loose material that has never settled into anything predictable. These are not places you casually build in. And yet, that is exactly where Artemis is heading. As we move into the late 2020s, the strategy has become more nuanced. Shackleton itself remains the long-term prize, but it likely won't be where we land first. Between the extreme slopes and difficult lighting, early Artemis missions will aim for more approachable nearby terrain. Places like the Nebula Rim or the Mare Massif, where you can operate safely while building up infrastructure. But even if Shackleton isn't where we plant the first flag this time, it remains the destination. Not because it is impressive, and not because it is difficult, because it solves a problem every first base has to solve before anything else. How do you stay alive without a constant billion-dollar umbilical cord of resupply from Earth? At the lunar equator, you are at the mercy of the day-night cycle. 2 weeks of searing heat, followed by 2 weeks of frozen darkness. That cycle turns power into your biggest engineering problem. You either bring enormous batteries, build nuclear reactors, or accept that your base will go semi-dormant for half its life. At the poles, the moon offers a different deal. Because of its tiny axial tilt, just about 1.5 degrees, the sun never climbs high overhead. It skims along the horizon. That creates regions sometimes called the peaks of eternal light, high ground that remains illuminated for most of the lunar year. And just a few kilometers away, down in the permanent shadow of crater floors like Shackleton, are cold traps where water ice has been preserved for billions of years. Water ice that we use to keep people and plants alive, and make air we can breathe, and just importantly, rocket fuel. This is the core logic behind the South Pole push. It's one of the few places where power and resources sit within reach of each other. Solar arrays on the rim, ice in the dark below, all close enough to tie together to a single operational system. It is the difference between flags and footprints in a place we can actually stay. Polar alternatives, redundancy, and expansion. If Shackleton is the frontrunner, it is not because it does alone. Indeed, while it is the preferred base site for later Artemis missions, it is not in our top 3 sites for the first Artemis landing, all of which are around 100 miles away from it. Shackleton Crater sits within a broad polar landscape that offers similar advantages, and in some cases fewer drawbacks. That matters more than it might seem at first, because building a presence on the moon is not just about picking a good site, it's about not depending on a single one. On the opposite end of the moon, the North Pole offers a strong counterpart in Peary Crater. Like Shackleton, Peary sits in a region where sunlight grazes the horizon, allowing certain high points to remain illuminated for most of the lunar year. It also hosts nearby shadowed regions that are likely to contain water ice. From a purely functional standpoint, that makes it a near mirror of the South Pole. Power and resources in close proximity, moderated temperature swings, opportunities for sustained operation rather than periodic survival. So why is Artemis not heading there first? A part of the answer is simply that the South Pole has been studied more extensively. Orbital missions have mapped Shackleton and its surroundings in greater detail, giving mission planners higher confidence in what they will find. When you are committing to your first long-term base, known quantities tend to win over equally promising but less well-characterized alternatives. There is also a clustering effect at the South Pole that is harder to match elsewhere. Around Shackleton, you do not have just one useful crater. You have multiple sites with overlapping advantages, elevated ridges with strong solar exposure, deep shadowed pockets likely rich in ice, nearby geological targets for science, potential communication high points like Malapert. It's a region where you can spread out and still remain connected. That said, Piri and the other polar regions are not backups in the sense of being lesser options. They are backups in the sense of being part of a future network. Once you move beyond that first base, redundancy becomes essential. You don't want all your fuel production, life support resources, and infrastructure tied to a single crater at a single pole. A second polar base, especially at the opposite pole, gives you resilience. If one side has a problem, the other can support it. If you're launching missions deeper into space, having propellant depots at multiple locations increases flexibility. There is also a strategic dimension that becomes more relevant over time. The moon is not large on a planetary scale. It is large enough that travel between distant sites is not trivial. Establishing footholds at both poles shortens distances, improves coverage, and creates a more distributed presence. Essentially, Piri represents something Shackleton does not the beginning, but the continuation. I think this is where the logic of site selection starts to shift. Shackleton is about making sure you can stay. A second polar base is about making sure you are not stuck. From there, the question no longer is simply, where can we survive, but rather, where can we grow? That is where the equatorial regions begin to matter again. Equatorial and Mare sites, the industrial moon. If the poles are about survival, the equatorial regions are about scale. Here we wish to move beyond a remote outpost into a place you can actually build things. Not just habitats, but infrastructure, roads, landing zones, processing plants, eventually even entire cities if you want to think that far ahead. The most obvious advantage is terrain. Large portions of the lunar equator are covered in Mare, vast plains of ancient volcanic basalt that have been smoothed over by billions of years. Compared to fractured, uneven terrain near the poles, these regions are almost welcoming. They offer wide, flat expanses that are far easier to land on, traverse, and develop. Take Oceanus Procellarum, the largest of these plains. It stretches across a huge portion of the moon's near side and offers something the polar regions cannot. Room. Room for landing pads, room for expansion, for large-scale industrial operations that would be cramped or impractical in a cratered polar environment. It also contains elevated concentrations of elements like thorium and potassium, which make it a valuable site for studying the moon's internal history and potentially exploiting certain resources. Nearby, Mare Tranquillitatis carries both symbolic and practical importance. It was the site of humanity's first steps on another world, but also represents a kind of baseline for lunar operations. We know how to land there, we understand the terrain, and importantly, the region includes access points to lava tube systems, giving you a bridge between surface operations and the kind of protected subsurface habitats you would eventually want to move into. Then there is Aristarchus Plateau, one of the most geologically diverse regions on the moon. It is rich in minerals like ilmenite, which can be processed to extract oxygen. That makes it attractive not just for science, but for industry. An ISRU-focused base here would not merely study the moon, but returning lunar material into usable products, the first step toward a self-sustaining economy. It is also one of the regions with elevated concentrations of thorium, a radioactive element that helps us trace the moon's internal heat and volcanic history. That makes it a scientific prize in its own right, but also hints at longer-term possibilities. While thorium itself is not immediately useful as a fuel without significant processing and infrastructure, its presence is a reminder that the moon is not just a place to extract simple resources like oxygen and water, but a place with a deeper and more complex geochemical story we are only beginning to understand. And for more rugged but equally valuable sites, Hadley Rill offers access to ancient lava channels and layered geological history. It is not as easy to build on, but provides insight into the moon's past and potential partial shelter in the form of cliffs and overhangs. At the equator, the day-night cycle dominates everything. 14 days of continuous sunlight followed by 14 days of darkness. During the day, surfaces can heat to well over 100 degrees Celsius. During the night, they can plunge below minus 100. That is not just uncomfortable, it is punishing for equipment, for materials, and for a system that depends on steady power. This means an Equatorial base must solve a problem that Shackleton largely avoids: energy storage. You need batteries, fuel cells, or reactors capable of carrying you through 2 weeks without sunlight. You need systems that can handle extreme thermal cycling without failure, and you need operational plans that account for long periods where conditions are far less forgiving. So why go there at all? Because once you solve those problems, the rewards are immense. Flat terrain makes construction easier, lower latitudes simplify launch trajectories for certain missions, and most importantly, these regions are far better suited to growth. You can build bigger landing zones, larger processing facilities, and more extensive infrastructure without constraints imposed by polar geography. In many ways, I think the Equatorial moon is where you can transition from surviving on the moon to thinking about using it for building up a spacefaring economy. Shackleton is the foothold, but places like Oceanus Procellarum and Mare Tranquillitatis are the industrial heartlands waiting to be developed. But even here, there is a limitation. All these sites still leave you exposed on the surface. And on the moon, the surface is not a particularly friendly place to live long term. Subsurface and lava tube sites, living below the surface. At some point, every plan for living on the moon runs the same quiet conclusion. The surface is not where you want to stay. It is exposed to radiation from the sun and from deep space. It is constantly bombarded by micrometeorites, most too small to see but still fast enough to do damage, and it swings between extremes of heat and cold that push even well-designed systems to their limits. You could manage all that for a while, especially with shielding and careful engineering, but if you are thinking in terms of decades or generations, the logic starts to shift. You stop asking how to protect the base of the surface, and instead start asking why you're on the surface at all. That is where places like Marias Hills come in. These regions are thought to contain enormous lava tubes, the remnants of ancient volcanic flows where the outer layer cooled and hardened while molten rock continued to move beneath it. When the flow stopped, it left behind vast hollow tunnels. On Earth, lava tubes can be impressive. On the moon, with lower gravity and no erosion from water or atmosphere, they can be enormous. Some may stretch for kilometers, with ceilings high enough to house entire structures inside. And more importantly, they come with built-in protection. A few meters of rock overhead can block most radiation. It can stop micrometeorites entirely. It smooths out temperature swings, turning the violent cycles of the lunar surface into something far more stable and predictable. Inside a lava tube, the environment starts to look less like space and more like a cave. The ones near the pores may also have ices in them too, and potentially pure sheets or hoarfrost. Still harsh, still airless, but manageable in a way the surface never quite is. We deep dive this in our episode Living in Lunar Lava Tubes, and they become impressive options, even if they aren't really ideal for base alpha. Nearby regions such as Lacus Mortis offer something similar, often in a more accessible form. Large pits in these areas are believed to be skylights, openings where the roof of a lava tube has partially collapsed. These provide direct entry points into subsurface spaces without the need for extensive drilling. That accessibility matters because lava tubes are not automatically easy to use. You still need to map them, you need to confirm their structural stability, you need to figure out how to seal and pressurize sections without risking collapse or leakage. You need to build infrastructure to move people and materials in and out efficiently. All that takes time, robotics, and a level of preparation that early missions may not be able to afford. And this is why lava tubes are rarely discussed as the first base, but rather we discuss them as the permanent one. In a likely sequence of events, surface bases come first, especially in places like Shackleton, where power and resources are readily available. Those early outposts provide the staging ground for exploration. Robots map subsurface structures, crews test access points, equipment is gradually moved underground, and then, slowly, the center activity shifts. The surface becomes a place you work, landing zones, solar arrays, communication towers, the infrastructure that connects you to space and to other parts of the moon. Underground becomes where you live. Habitats expand within shielded spaces. Temperature control becomes easier. Radiation exposure drops dramatically. Over time, the difference between a temporary outpost and a true settlement becomes less about location on the moon and more about whether you are above the surface or below it. So while places like Maria's Hills and Lacus Mortis might not headline the first wave of missions, they are likely to be popular spots in a more mature lunar civilization. Not a cluster of habitats clinging to the surface, but entire communities carved into the rock beneath it. And if subsurface habitats answer the questions of how we live on the moon, the far side begins to answer a very different question. What do we do when survival is no longer the primary concern? Far side sites. The Observatory moon. If the poles are about survival and early permanence, and the Mare are about industry and expansion, the far side of the moon serves a very different purpose. It is quiet. Not visually. The terrain is just as battered and complex as anywhere else. But in terms of radio noise, it is the most silent place in the inner solar system. The moon itself blocks Earth's constant stream of radio emissions, from broadcast to radar to endless background chatter of modern civilization. Even satellites in most Earth orbits cannot easily interfere. That makes the far side something unique. It is the one place nearby where we can listen to the universe without hearing ourselves. Sites like Mare and Genii begin to stand out immediately in that context. While smaller and less uniform than the great Mare of the near side, it offers relatively stable terrain for deploying instruments. More importantly, its location makes it ideal for radio astronomy. Arrays spread across its surface could observe wavelengths that are nearly impossible to study from Earth, opening a window into the early universe, solar activity, and distant astrophysical phenomena. Further afield, regions like the Compton-Belkovich complex had a different kind of value. Its unusual chemistry makes it a rare geological target, hinting at processes that were not common across the rest of the moon. A base here would be less about expansion and more discovery, answering questions that cannot be resolved anywhere else. But the real transformation comes when you consider what kind of observatories the moon allows us to build. On Earth, telescopes are limited by the atmosphere. Even the best adaptive optics can only compensate so much. In orbit, we can escape the atmosphere, but we remain constrained by size, stability, and cost. Every kilogram launched into space is expensive, and building truly massive instruments becomes a challenge. The moon changes that equation. Low gravity makes larger structures easier to support. No atmosphere means no distortion, and the far side radio silence gives you a clean observational environment that does not exist anywhere else nearby. This is where concepts like zenith telescopes become especially compelling. A zenith telescope does not need to track objects across the sky, it simply points straight up. On Earth, these are often built using liquid mirrors, where a rotating fluid naturally forms a perfectly smooth parabolic surface. They are simple, stable, and can achieve remarkable precision. They are limited by weather, atmosphere, and location. Needless to say, using a liquid mirror is a bit harder in that environment, but those other normal limits go away. You can build larger mirrors supported by lower gravity. You can place them in permanently shadowed regions to maintain stable temperatures. You can operate them continuously without atmospheric interference. And on the far side, you can pair them with radio arrays that stretch across kilometers, all shielded from Earth's interference. So we're not just building a better telescope, we're building one we cannot put anywhere else. You could study the cosmic dark ages at wavelengths that never reach Earth's surface. You could monitor the sun in deep space with unprecedented clarity. You could build instruments that would be impractical or impossible to deploy anywhere else. Of course, all of this comes with trade-offs. The far side is isolated. There is no direct line of sight to Earth, which means every mission requires relay satellites to maintain communication. Logistics becomes more complex. Rescue operations, if needed, are more difficult. Even coordinating with other lunar bases adds an extra layer of infrastructure. Which is why far side sites are unlikely to host the first major base. They are not about making it easier to survive, they're about making it worthwhile to stay. In a more advanced lunar network, the far side becomes something like a dedicated scientific zone, a place where the infrastructure built elsewhere supports activities that can only happen there. Power generated at the poles, materials processed at the Mare, habitats carved into lava tubes, all feeding into observatories that take advantage of the moon's unique position. If Shackleton represents the beginning of human presence on the moon, the far side represents its expansion into something more ambitious, not just living off the moon, but using it to understand the universe beyond. Civilization does not usually end because one thing goes wrong. It ends because one rare catastrophe arrives before anyone has built the tools, backups, and redundancies to survive it. Ice ages, solar flares, rogue planets, supernovae, lost archives, failed recoveries. These are not just disasters, they are stress tests for whether a civilization has become durable. That is the idea behind my new Nebula Plus collection, Cosmic Catastrophes and Survival. It gathers my Nebula-exclusive episodes on extinction risks, planetary disasters, civilization backups, and rebuilding after collapse. This month's new edition is Nearby Supernovae. Could one destroy Earth, and could we stop it? Where we look at whether exploding stars have threatened Earth before, which nearby stars might eventually explode, and whether a future civilization could shield itself, move the danger away, or harvest the aftermath. If that sounds like your sort of rabbit hole, you can find the full collection on Nebula, along with years of SFA exclusives, collections, bonus episodes, and regular episodes early and ad-free. My link or the QR code gets you 50% off an annual plan, or 40% off lifetime access. The Lunar Network. By this point, the question has shifted. It ceases to be where should we build a moon base, it becomes what do we want that base to do. Because each of these locations is solving a different problem. Shackleton and the polar regions focus on continuity, give you power and water close together, making it possible to establish a foothold that does not depend entirely on Earth. They are about survival first and everything else second. Polar alternatives like Piri extend that idea into resilience. They reduce risk, distribute infrastructure, and make the system more robust. Once you're committed to staying, redundancy becomes just as important as efficiency after all. The Equatorial Mare shift the focus to scale. They are where you build large systems, process materials, and expand beyond the constraints of a single site. They are less forgiving, but far more flexible once you can manage their challenges. Subsurface regions change the equation again, moving from temporary survival to long-term habitation. They offer protection and stability in a way the surface never quite can, and they likely become the backbone of an enduring settlement. And the far side pushes beyond survival and expansion into purpose. It is where the moon becomes a platform for science, a place that enables things we can't do anywhere else nearby. Seen this way, the moon does not have a best location. It has a sequence. You begin where survival is most likely easiest, even if construction is harder. You expand to where building is easier, and if survival is harder. You move underground when you are ready to stay, and outward when you are ready to explore. Shackleton sits at the beginning of that sequence, not because it is perfect, but because it gets you through the first and hardest step, staying. Not one, but many. We often talk about the moon base as if it would be a single place, a single cluster of habitats somewhere on the lunar surface. That is not how it is likely to unfold. Yes, you would likely see some bases expand far more quickly than others, becoming cities rather than outposts, but not singular bastions either. After that first base is well established, the moon is simply too large, too varied, and too useful in too many different ways for that. What begins as a base at Shackleton becomes a network of sites, each chosen for what it does best. Power stations at the poles, industrial zones across the Mare, habitats beneath the surface, observatories on the far side. Each one is solving a different problem. Each one enables the next step. Shackleton matters because of where the process can begin. It is where we first combine energy, resources, and access in a way that makes a sustained presence possible. But it is not the destination. It is the opening move of humanity's grand saga on the moon, and our gateway to the stars.